Harnessing the power of quantum mechanics, scientists have successfully achieved the remarkable feat of making quantum bits fly. Greetings, everyone. Today we will be delving into an intriguing subject. Specifically, we will be exploring the groundbreaking work of two physicists from the University of Konstanz. These brilliant minds have devised a theoretical framework that enables the secure exchange of information within quantum computers, utilizing photons as the primary mode of transportation. By employing stimulated Raman emissions, they have successfully transformed the information stored in a material qubit into a photon, granting them enhanced control over these particles of light. Notably, their innovative approach empowers them to manipulate the direction, velocity, and location of the information flow. In February 2024, the researchers published a comprehensive account of their methodology in the esteemed journal Physical Review Research. Now, without any further delay, let us embark on our captivating discussion. The advancement of information technology is anticipated to take a significant leap forward with the introduction of quantum computers. These revolutionary machines have the potential to tackle computing problems that are currently beyond the capabilities of conventional computers or would require an exorbitant amount of time to solve. Research teams all over the globe are diligently working towards the realization of practical quantum computers. However, this endeavor is far from simple, as the fundamental building blocks of these computers, known as quantum bits or qubits, are incredibly delicate. One type of qubit, for instance, relies on the spin of a single electron, which operates on an atomic scale. Maintaining the stability of such a fragile system is already a daunting task. The challenge is further amplified when it comes to establishing connections between two or more of these qubits. Consequently, the question arises, how can a reliable exchange of information between qubits be achieved? Physicists Benedict Tissot and Guido Burckhardt from Konstanz have devised a theoretical framework that outlines how qubits can exchange information using photons as a mode of transportation for quantum data. The fundamental concept involves transforming the information content, specifically the electron spin state, of a material qubit into a flying qubit in the form of a photon. Photons, known as light quanta, serve as the fundamental constituents of the electromagnetic radiation field. The novel aspect of this model lies in the utilization of stimulated Raman emissions to convert the qubit into a photon, enabling greater control over the photons themselves. Burckhardt elaborates, stating, "We are proposing a paradigm shift from optimizing the control during the generation of the photon to directly optimizing the temporal shape of the light pulse in the flying qubit." Drawing a parallel to the internet, Benedict Tissot likens the fundamental process of a quantum computer to that of a traditional computer. In a conventional computer, information is encoded as bits and stored on a chip using electrons. However, when it comes to transmitting information over long distances, the content of these bits is transformed into light signals and transmitted through optical fibers. Similarly, in a quantum computer, the exchange of information between qubits follows a similar principle. The information needs to be converted into states that can be efficiently transmitted, and photons prove to be the ideal medium for this purpose, as Tissot explains. According to Tissot, there are various factors that need to be taken into consideration. The goal is to have authority over the flow of information, including the direction, timing, speed, and destination. To achieve this level of control, a system is required. The researchers have developed a method that utilizes resonator-enhanced, stimulated Raman emissions. This method involves a three-level system resulting in a multi-stage process. These stages provide physicists with the ability to manipulate the created photon. Tissot explains that there are more options available, allowing for greater control over the photon. The utilization of stimulated Raman emission as a means of communication is a well-known practice within the field of physics. Nevertheless, employing this technique to directly transmit qubit states is not a common occurrence. The introduction of this novel approach has the potential to mitigate the impact of environmental disturbances and undesired repercussions stemming from abrupt alterations in the temporal structure of the light pulse. As a result, the conveyance of information can be executed with greater precision. A comprehensive outline of the methodology was documented in the February 2024 edition of the scholarly publication, Physical Review Research. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.